let's now look at our second case where we have real and repeated poles in our function f of s. So let's suppose that our f of s has repeated poles at some point s equals negative p. And so what this would look like is we would have f of s equals some numerator polynomial, and in the denominator we're going to have, to generalize, let's say we have s plus p to the power of n. And so we might also have some other things in the denominator as well, which we would need to account for. But for this case, what we're going to do is, I'm just going to show our sort of expanded version here. So if we use our partial fraction expansions, we're going to have k sub n divided by that s plus p to the power of n. And then we're also going to have a term as we drop that exponent by 1 all the way until it goes away. Or until it goes to 1 rather. So we have s plus p to the n minus 1, and that coefficient we can call k sub n minus 1 plus dot 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 all the way down to, let's say we have a k2, and that's going to be s plus p squared plus k1 divided by s plus p, and that quantity s plus p is just to the power of 1 now. And then to account for any other parts of our denominator, we can also say we have plus f1 of s, where this f1 of s right here is just going to be any part that doesn't have a pole at s equals negative p. So this accounts for parts that, or a part that doesn't have pole at s equals negative p. So in this case, we would say we had n poles at negative p, and so I think that'll be more clear when we look at our numerical example in the next video. So just like with our case 1, we have this problem of we want to find these residues of f of s. We want to find our k sub n minus 1, all the way down to k1. And so our kn, we find the same way as we did with case 1. So let's just say we find k sub n the same way as in case 1. And so what we do then is we're going to multiply both sides by that s plus p to the power of n. So multiply both sides by s plus p to the power of n, and then we're going to evaluate at s equals negative p. And so what that's going to do is, of course, is going to make every term except for the one associated with kn go to 0. So we can say then that kn is equal to s plus p to the power of n times f of s evaluated at s equals negative p. And so again, we can think about, as we're multiplying both sides up here, we have an s plus p to the power of n, which is going to cancel out here and here. We have an s plus p to the n, which is going to cancel out all but 1, so we'll cancel out all of these and we'll still be left with an s plus p in the numerator, such that that is going to go to 0 when we evaluate at negative p. And so that's going to be true for all of these terms that have a pole at p as well. And so in that sense, we say that this is the same sort of approach that we took when we were dealing with our case 1. However, we can't continue to do that as we look for this k sub n minus 1, k sub n minus 2, and so on. So what we need to do then is we're going to keep the same sort of first step. So let's say now we want to find our k sub n minus 1. So to find our k sub n minus 1, what we're going to do is we're still going to multiply by that same factor. So multiply both sides by our s plus p to the power of n. But now, remember, when we do that, what we're going to be left with is something like this. Let me do it in a different color here. So we have f of s times s plus p to the power of n is equal to, we have just the kn, and then we're going to have plus s plus p times kn minus 1, and so on and so forth. And so what we notice is now we're looking for this kn minus 1. We don't want this kn. So what we can do, that's sort of a clever way to get around this, is we can take the derivative of both sides. Because this k sub n is just a constant, taking the derivative of that value is going to make it go to 0. And here we have our residue multiplied by an s, so our result is just going to be the residue. So what we can say then is we're multiplying both sides by this s plus p to the power of n, and then we take the derivative. So take the derivative of both sides. And what that does is that gets rid of our constant k sub n. And then once we've done that, we then evaluate at our s equals negative p. So evaluate at s equals negative p just like we did before. So what that looks like is we would say k sub n minus 1 is equal to the derivative with respect to s of s plus p to the power of n times f of s. So we take that derivative first, and once we've taken that derivative, we then evaluate it at s equals negative p. So that's how we would find our k sub n minus 1. So doing a similar process for k sub n minus 2, we could say again we're going to multiply by our s plus p to the power of n, but now we want to get rid of our k sub n and our k sub n minus 1. So what we end up doing is differentiating twice. So just writing the result of that, we would have k sub n minus 2 is equal to, and we also have this 1 over 2 coming out, and I'm going to write 2 factorial to make it easier to see, to relate to our general form here in a little bit. But now we have the second derivative with respect to s twice of s plus p to the power of n times f of s. And again, after we've taken that second derivative, we then evaluate at s equals negative p. So of course what we can do is we can generalize. We sort of see a pattern here. And so generalizing, we can say k of n minus m is equal to 1 over m factorial, and then we take the mth derivative with respect to s of s plus p to the power of n times f of s, and again after we've taken all of those derivatives, we need to evaluate at s equals negative p. So this is a general form for our coefficients for this real and repeated poles case. And in this case, our m is equal to 1, 2, so on, all the way up to n minus 1. And so what we can see here is we can match this to our m equals 1 case would be up here, and this would be our m equals 2 case over here. And so if we're using this general equation, an important thing to be able to do is identify what your m value is and what your n value is, so that you can plug in the appropriate way. So in terms of doing our inverse Laplace transform, we can sort of modify a little bit. So we're considering then, once we know our kn value and our k sub n minus 1 and all of our k values in this equation here, we can sort of generalize how we would take our inverse Laplace transform. So I'm going to show you a slightly modified transform pair from what's in the book. So if we want to take the inverse Laplace transform of 1 divided by the quantity of s plus a to the power of n, we can say that this is Laplace transforms to t to the power of n minus 1 times the exponential e to the negative at divided by the quantity of n minus 1 factorial times our unit step function u of t. And so again, this is a slightly modified version of entry number 7 in the table in your book, which is on page, or sorry, not page, I have a table number here, which is on table 15.2 in the textbook. So just write for clarity, this is a modified version of that entry. And so we can use this to then give us a general form of our f of t to where we can just plug in our k values. So we know that our f of t is going to be equal to, in this case, a k1 times e to the minus pt plus k2 times t e to the minus pt plus k3 over 2 factorial t squared e to the minus pt. So notice our e to the minus pt is staying constant, and plus so on and so forth all the way up to k to the n, or sorry, k sub n divided by the quantity of n minus 1 factorial t to the power of n minus 1 times e to the negative pt. And all of that is multiplied by our unit step function u of t. And then we also are going to add in our f1 of t, where we have our f1 of t is just our Laplace transform, or rather our inverse Laplace transform of our f1 of s. So f1 of t is equal to our inverse Laplace transform of our f1 of s. And so coming back up here, remember our f1 of s was just this component that did not have any repeated poles at that negative p. So this would be our general form that we could use for our f of t. Once we find our values of k, we can just plug it into this expression.